it's quite funny that particle physicists, they all bring up exactly the same talking points with exactly the same language. And I think there's a deeper reason for that, which is that you all listen to each other too much.
We spend far too little on R&D as it is, and we should be making the case for why we need to invest in science in general, as together, rather than saying, "Oh wait, let's shut down particle physics because then maybe there'll be money available for something else."
Should we spend tens of billions of dollars on a new particle collider, a successor to the LHC called the FCC, or Future Circular Collider? That's what CERN wants to do. And today we're going to debate whether they should. Arguing the case for the FCC, we have Harry Cliff, a particle physicist working at CERN and the University of Cambridge, who presented the case for the FCC at London's prestigious Royal Institute and is the author of the book Space Oddities and How to Make an Apple Pie from Scratch. So welcome, Harry.
Hi, Phil. Nice to be here.
And to argue against building the FCC, we have Sabine Hossenfelder, a physicist, author of over 80 scientific papers, one of the world's leading science popularizers, and she is the author of the books Lost in Maths and Existential Physics. So welcome, Sabine.
Hi, guys. Good to see you.
Now, if you like these sorts of debates, do check out my Science Debates playlist. We've got Alan Guth debating Roger Penrose on inflation versus cyclic cosmology. We've got Carlo Rovelli debating Nobel Prize winner David Gross on strings versus loops. We've got all kinds of other science debates. And also, I have a book, The Battle of the Big Bang, which I've co-authored with Sabine's former colleague at the Perimeter Institute, Nia Afshori, and that focuses on the battles, how to interpret the Big Bang, what might have come before. So if you're interested in those, I'll have links below. All right, so let's kick the debate off. Harry, why don't you start us off? Lay out the case for the FCC.
Well, let's set the scene. So where are we in particle physics at the moment? The major thing that happened 15 years ago, almost 15 years ago now, was the discovery of the Higgs boson. So that happened at the LHC quite early on in its run. It's been going for, a decade and a half now. And that was the last particle expected in the Standard Model, which was missing. So the Higgs kind of completes this theory we have, the Standard Model of particle physics, which describes the fundamental ingredients of our universe and how they interact with each other, with the exception of gravity. But it describes the other three fundamental forces. But we have very good reasons to think the Standard Model is not a final theory of the universe. And we have observational evidence, things like the existence of dark matter, which is very well established in astrophysics and cosmology. Things like the fact that the universe actually contains matter at all is difficult to explain in the context of the Standard Model. Maybe we'll get into some of these problems in a little bit. I suspect we will. But there are also things about the Standard Model itself that are rather strange. There's this pattern of masses in the matter particles, things like the electron, the quarks, which are not understood. They have these kind of patterns that suggest they come from something deeper, a bit like the periodic table of the chemical elements in the 19th century hinted at atomic structure. So there are all these little bits of circumstantial evidence suggest this theory is not the final story. So as well as these very clear observational bits of evidence, there's more to find. So the question is, how do we make progress? Now, what has happened at the LHC is we found the Higgs, but we haven't found yet any signs, really solid signs of new physics. And that's left us in a really strange, probably unique position, at least in the last century, in that we do not have a clear target for the next machine. With the LHC, when that was being planned, it was kind of known, you were guaranteed if you probed the energy scales that the LHC was designed to probe, you would find either the Higgs boson or there would have to be something else that did a similar job. So you were kind of guaranteed to see something. Now, with the next collider, the question is, what might you see? And the crux of the argument for the next machine is around the Higgs boson itself. So this new particle, it is really unique in the Standard Model. It's what we call a scalar boson, which means it has no spin, and it sits at the center of many of these mysteries and is potentially connected to the origin of matter in the universe, potentially connected to dark matter, but also we don't actually know whether this Higgs particle that has been found is the Standard Model Higgs boson yet. We haven't measured its couplings to all the different matter particles. We don't understand the mechanism that gave rise to it in the early universe. And we don't actually know if it is a fundamental particle. There is a chance this thing, whereas it's quite possible the Higgs is not fundamental. And the LHC at the end of its run will leave us with a fairly blurry picture of the Higgs, where we kind of know it's there. We'll have measured some of its properties, but not at the detail we require to really know if this is the thing predicted by Higgs and Englert and Brout in 1964 or something more exotic. So the primary goal of the first version of the FCC, which is an electron-positron machine, is to make millions of Higgs bosons in a really pristine experimental environment and make high precision measurements of this particle. And the hope is that by doing this, we will confirm, is this the standard model Higgs boson? Or if not, we'll get a clue to the larger theory that comes after the standard model. So that's really the core of the argument. But the kind of broader thing is that, colliders are like telescopes, where you might build a telescope to look for a particular thing, but you almost always see other things in the sky as well. So the Higgs is at the center, but it's also about making precision measurements of other particles like the Z boson, W bosons. These are particles of the weak force, studying different types of quarks and their interactions, all of basically this suite of precision measurements. And by doing this, we really kind of solidify our understanding of the standard model. And if there is new physics to be found, it gives us indirect evidence for its existence, potentially reaching energy scales far beyond what we can probe directly at colliders, even in the most ambitious long-term vision of what the future collider might achieve. So it's really about understanding the Higgs boson and giving us the best possible set of evidence or ways of searching for, in a very broad sense, what new physics might be out there.
All right. Thanks, Harry. All right, Sabine, lay out the case against the FCC.
Yeah, I think that building this huge collider at CERN would be a mistake for the foundations of physics, for science overall, and also for society. It's a huge investment. You said somewhat vaguely, like tens of billions of dollars, which I think is correct. Like, if you want to build the whole thing, we're talking about something like 40 billion optimistically. And I think it's a high risk, low turnout thing. Like, even in the best case, what do we get out of it? So as Harry just said, like the solid case for the FCC is that it'll probe the Higgs boson better. Basically, we will get out more data with higher energies. We would probably see more events. We'd be able to measure the self-interaction, stuff like this. But how is the Higgs boson actually connected to all these big mysteries that you mentioned? By the way, on some of which I disagree that there are even mysteries. There's absolutely no evidence that the Higgs boson is actually connected to any of those. Like, I know there are theories, but, theoretical physicists have theories about everything. So there's no evidence that the Higgs boson is connected to dark matter or to dark energy or to the origin of the universe or to anything in particular. So to me, it's like the default expectation for what it come out if we were to build the thing is that we learn a few constants about the Higgs boson higher precision. And I think that's not enough to justify the investment of such a huge amount of money. It's also the headache that I get when thinking about the FCC is that if we put that much money into this one project, it's going to attract a lot of smart people because it'll generate positions. And the people who work on this will not be available to work on other stuff. I know a lot of people say, well, but then we'll just have more jobs and there'll be more intelligent people working in the foundations of physics. But I think there are only so many intelligent people on the planet. So if particle physics sucks them all up, then there'll be fewer intelligent people working on things that I consider to be more important. And that's other parts of the foundations of physics, other parts of science, and also other parts of society overall. So this is why I think it actually has a downside, putting that much money into an area that at the moment has so little promise. It's not that I'm against particle colliders per se. I think there's a strong case to be made, like if particle physicists would manage to shrink down their particle colliders to a reasonable size. Like, we're talking about a project, what's the current status, like 91 kilometers in circumference? That's crazy. And there are technologies that are working on that could shrink these things down. Like, we could talk about this in more detail, like wake field acceleration, or maybe they'll eventually find a room temperature superconductor and stuff like this. This could all help, but these technologies aren't there yet. So my sense at the moment is we're missing a good justification. Like if we actually had astrophysical data that would say, yes, it's a particle and it's in the range that the next collider could reach, that would be a strong case, but we don't have such a case. Like this is just to give you an example.
Or sorry, Sabine, when you say it's a particle, are you referring to dark matter or what?
Yeah, dark matter. Yeah. I mean, Harry made it sound like it's a settled thing that dark matter actually exists and it's made of a particle. Well, I disagree. As you probably know, there's this alternative explanation that we got something wrong with gravity. But even if you believe that it's a particle, at the moment, I think even the particle physicists favor the idea that it's a very light particle. And you wouldn't look for something like that with high energy collider. That doesn't really make any sense. Like the signal there's a high risk it would just get lost somewhere in all the stuff that gets produced in these collisions. So, but what I meant to say is like if we had a strong clue that it's, I don't know, a WIMP with a mass of like 10 TeV or something, I'd say, yeah, build the thing and then we'll know, right? Then when we have it, in our detectors. But that's not the situation we're in. And so this is why I'd say it's at this moment in time, it's not a good thing to do.
Right. Okay, Harry, quite a few points there. I don't know where you want to go first.
Yeah, I mean, maybe I'll start with the last one about dark matter. I'm no one's putting dark matter at the heart of this case, right? It is about the Higgs boson. And the way I would frame it is, we have discovered a new fundamental property of the universe. And are we just going to, go, okay, well, we know it's there. We're not really going to show any more interest or curiosity in this thing. I mean, the reason the Higgs is important ultimately is there was this phase transition that took place in the very early universe between about a trillionth of a second and a tenth of a nanosecond after the Big Bang, where this field, which we call the Higgs field, underwent this transition where it acquired this kind of uniform value throughout space. And that uniform value is what gives mass to the matter particles that we're made of, the fundamental particles. And it caused the forces that we know, the electromagnetic force and the weak force, to emerge from a unified force. So it set the rules of the game, basically established the current set of particles and forces that we have in the universe. And the Higgs boson is a byproduct, effectively, of that process we believe happened. But we haven't yet actually probed how that mechanism occurred, how it took place. And the FCC will probe, basically technically the form of what we call the Higgs potential, which will tell us how this transition occurred. Did it occur in the standard way that is predicted by the standard model, or is it something more exotic? And that in of itself is a fundamental thing that happened in our universe. And I think it's, that on its own is a fascinating thing to try to understand. But it also is potentially connected to other issues like the origin of matter in the universe. So it's not that we're saying, we're definitely going to discover dark matter. We will do loads of measurements that will give us sensitivity to dark matter potentially. So we might be lucky and find it. But Sabina's quite right. It may be in a regime, if it is a particle, that is outside the sensitivity of the FCC. But what we're trying to do is design an experiment that gives us the maximum possible opportunities to make new discoveries. And the Higgs in particular is this fantastic unknown quantity that gives us many, many possible avenues for discovery. And that's why many people think this is a promising idea. As I said, again, these colliders are they're not single target. We're not just going to learn about the Higgs boson from a future collider. You will learn about a huge range of fundamental processes. So to give you an example from the LHC, it's true that we've not discovered, supersymmetry or micro black holes or all of these exotic things that people were talking about a couple of decades ago. But what we have learned is we've learned a huge amount about the standard model. We put really strong constraints on how, say, the quarks couple to the weak force, but we've also found new sorts of states that we didn't know about before. So when the quark model was proposed in the 60s, Gell-Mann actually suggested you would find basically different combinations of quarks in 2s and 3s, but he also mentioned things called tetraquarks and pentaquarks, which had never been seen before, but we've now discovered dozens of these things at the LHC. So we're improving our understanding. It's not kind of, shattering new physics that transforms the fundamental understanding of the universe, but we're building on our understanding of particle physics. The other thing I'd like to pick up on is this point about cost. So the FCC is a 2-phase project. And I think all we should really seriously talk about at the moment is the first stage, because that is going to take us up to the 2050s to try and think about, whether we build the final version in the 2070s is, I'll probably be dead by then. So I'm not going to worry about that too much. But the first phase is this precision E plus E minus machine. The cost of that is about 15 billion euros, or Swiss francs, more or less the same thing, which is a lot, undeniably. But when we talk about these big numbers, we have to understand, the timescales and the way these costs are spread. So this is over about 15 years. So you're talking about $1 billion a year spread over at least the 23 member states of CERN. It probably actually, to build it, we will need to involve other international partners, whether that's Japan, the European Union, whoever else. But if we just said, okay, the CERN 23 member states are going to pay for this over 15 years, that comes to about €1.90 per year per person in the EU. So these are, they're vast sums of money on it in terms of scientific investment, but they're not vast in the terms of government spending. It's noise on the government budget. If you think about, I think we shouldn't let the fact that it's 90 kilometers scare us. It's obviously very big, but the size in itself is not a problem if you can deliver it within a reasonable timescale and a budget. And I think, what the studies have shown is that this is an achievable machine with technology that can be developed in the next decade or so. And the final thing, so for Sabina's point about it sucking up all the clever people, I mean, there are about, 15,000 people working on the LHC or more or less. I imagine it would be a similar sort of number on a future collider. Are you really saying there's only 15,000 smart people in the world in a world of 8 billion? I think there's plenty of scope for people to work on other things. And I don't think we're going to kind of, gobble up all the brains who will be available to solve other problems just from this one future project.
All right, Sabina, 3 topics then. One, it doesn't matter if they discover dark matter or not because the Higgs is so exciting. There's lots of potential for new discoveries. The second is the cost isn't as bad as the headline sounds. And the third is, there's plenty of smart people, nothing to worry about. How do you respond to those 3 points?
Okay, well, let's start with dark matter. You made it sound like if we don't build this thing, we're giving up on dark matter.
No, I didn't say that at all. No, I'm actually not saying that.
That's literally what you said. You said, are we giving up on dark matter? So...
No, I didn't. I certainly didn't mean to imply that. Maybe I missed.
Maybe I misheard it. Well, you have it on record, so you can check.
Yeah. Well, certainly not what I meant to say. That I'm not saying that at all.
Well, let's just clarify. What are you saying? Dark matter.
I'm saying, we're not predicating the case for the FCC on finding dark matter. So the core of the argument is the Higgs boson. Ultimately,
okay.
But the purpose of the machine. Not purpose, but the machine will give us many opportunities to make measurements that could give sensitivity to dark matter. We might be lucky. Dark matter might be of a nature that allows us to see it at this new machine or see indirect evidence of it in some way, but it may not. So it's not a sure thing by any stretch. I'm not saying we'll learn nothing about dark matter. We'll rule out lots of various models. We'll close the parameter space off at worst, but there's absolutely no guarantee we discover it. And I'm not going to claim that anything different.
Okay. All right. Sabina.
Yeah, of course, I totally agree with that. But you see, the problem I have with particle physicists is that they start opening up with alluding to these big open problems that we have in the foundations of physics, like dark matter, the origin of the universe. Sometimes they even bring up dark energy, or that there's supposedly something mysterious with the patterns of masses in the standard model, which I just disagree with, and so on. And then if you push them on it, they'll admit, actually, probably the thing isn't going to tell us anything about it. And this is exactly the case with dark matter. So I think that at the moment, the thing to do to look for dark matter is to collect more data from astrophysics, which is already what we're doing. So building a bigger collider is not the right thing to do if you want to study dark matter at this point.
Can I come back on that just a little bit? I mean,
very briefly, Harry, because I want Sabina to address your other 2 points.
Sorry, just to say on the dark matter point. We don't know what dark matter is. We have to be, so I think any method you have of searching for it, whether that's direct detection, whether it's astrophysical, whether it's colliders, it's really about giving us the best chance of learning something, right? So we're in a position of ignorance. So to sort of say, well, it's not worth pursuing one avenue because it might be wrong, but that's what science is. It's, you never have a surefire discovery. The reason you do experiments is to find out what's there. Now, I'm not saying this is the core of the argument, but it does give us an opportunity to learn something about dark matter, perhaps.
Okay,
right.
Sabina, want to reply to that, and then we'll go to the other
look, you can say this about every experiment, right? So we always have to look for something. So we should fund all possible experiments? Certainly not. So we have to figure out a way to make a decision, like which is the one that we actually fund. And what I'm saying is that at the moment, this particular experiment is not a good investment because there's a high risk we're not going to learn anything interesting from it, or at least nothing that anyone except particle physicists are interested in. I mean, as you pointed out correctly, the LHC has delivered other data than the Higgs boson, like composite particles, like the tetraquarks, and, taught us something about the structure of the proton, or God knows what. But most people, let's be honest, don't care about it, right? And I think they're still a little bit pissed off that particle physicists, for like 10 years before the start of the LHC, went around and said, it's going to tell us something about dark matter. It's going to find supersymmetry or string theory or make contact to parallel universes or whatnot, none of which happened, of course. And particle physicists haven't explained what went wrong. And so they just didn't deliver. And now they say, well, we want a bigger collider. And I'm like, okay, guys, you have some explaining to do. So that's my take on this. At the moment, looking for dark matter, yes, it's a good idea. We should do it. Definitely, we should not give up on it. But building a bigger particle collider is the way to do it. So about this other thing with the cost, I honestly don't really understand this argument. You could say this about anything. You can take any kind of expense that your government is going to make and divide it by whatever you want, number of people, number of years, and then the number's going to be smaller. I still think it's a lot of money. I actually think no one really disagrees on that. If you compare it to other experiments, like even if you take the biggest telescopes that NASA has planned or something, it's still more expensive than that. And that is for only the first stage of the product. It's already more expensive. And also, like this first stage, second stage argument, this is obviously just a way to try to get people to swallow the idea of actually handing out the full 40 billion. Because once they build the first thing, they say, well, look, we already built the first stage. Now we should also build the second. And I also think actually for particle physicists, at least, it's my understanding, like my sense of what they're up to. It's like the big project, like the one on the TV, big bang, boom machine, is like the key motivation to actually doing the thing. And then, the Higgs factory would be nice, but really we want the big thing. And then the third point, the smart people. Well, so you're saying, do I really think that there are only 50,000 smart people? Well, it's a bell curve, right? So depending on where you put the cutoff, there'll be fewer and fewer people. So, and the more people you need, the more you dilute the IQ pool, so to speak. But let me put this differently. I actually think there aren't all that many smart people who are interested and also motivated to work at the foundations of physics. And if particle physics is taking up a lot of them, then there'll be less for other things that I personally think are more relevant or more promising at the time, such as the foundations of quantum mechanics. Or we can talk about the details, but just generally, there's also his historical part of this that maybe I should add. I think particle physics has historically, because of the relevance after the Second World War, grown into this really huge field. And I think it's at the moment, it's really overinflated and it needs to shrink back to a reasonable size. It's not like I think it needs to die, but I think that there's too much money going into it, that too many people going into it, and we need to bring it down to a reasonable level.
Right, Harry, I want to get to this question of the cost, because you say, well, it's the equivalent of like a cup of coffee or something for each person. But as Sabina pointed out, any project could do that.
Yeah.
Other big science projects, I'm thinking, for example, LISA, the Gravitational Wave Observatory they're sending into space. That's a big project. I think the budget's about 2 billion euros or something. Is that right? Something like that.
I'm not sure.
Yeah. So these are the sorts of budgets big science projects gets, like 1 or 2 billion. Isn't 15 billion Swiss francs, about $17 billion, like crazy amount?
I mean, I think the question is not, the absolute size of the budget. I think does it deliver a scientific, kind of benefit commensurate with the money you're spending? That's the real question. Okay. So, you might spend 2 billion on LISA. I suspect it might be a bit more than that, actually. James Webb was an order of billions as well, I think. A square kilometer array also in the billions. So it's not totally beyond the realms of other projects that exist. The LHC, depending on how you top the numbers up, is about 12 billion. So it's actually the first phase is similar, a bit more than the LHC.
Actually, let me interrupt. Can we just explain these two phases? We haven't.
Sorry, that's a good point. Yeah.
Let's explain that.
So phase one is what's called the FCCEE. EE stands for electron, or electron positron. So it's an electron positron collider, and the particle physics historically has kind of progressed where you have a hadron collider like the LHC. They're very good for getting to high energies and discovering new particles. And then you have an electron positron machine often that's for doing precision measurements. And the reason that you build one of these things is that when you collide two protons at the LHC, a proton's not fundamental. It's made of quarks and gluons. So when you collide and you get this mess, this almighty mess everywhere. And it's a big challenge to extract kind of precise measurements from that kind of machine. Actually, with the LHC, we've done much better than we expected. There were lots of measurements people thought were impossible 15 years ago at a Hadron Collider that have proved to be possible because people come up with very clever techniques of getting signals out of this messy data set. But in an electron-positron machine, you have these two fundamental particles. They annihilate, and then they create whatever final state they create in this clean environment. So you get, for example, the way the Higgs will be produced is in coupled with a Z boson. So you get a Z boson and a Higgs produced, and nothing else is the idea. So you can then get this really clean environment, really precise measurements of the Higgs. So actually, this machine will make, I think, millions of Higgs. The LHC will have made more than that, but we'll miss most of them because they're hidden in all the other rubbish that gets produced in the collision. So that's phase one, and it's really it'll run over several years. It will run at different energies. It will make lots of Z bosons first, which are a force particle of the weak interaction. You can do lots of interesting physics with that, push down your precision by a couple of orders of magnitude in many cases there. And maybe the other point I sort of make, you don't just discover new physics by seeing a new bump in a graph and saying, there's a new particle. Very often in high energy physics or particle physics in general, discoveries have been made indirectly before you see the particle directly. So this is basically where you make very precise measurements of certain properties of particles. You compare to your theoretical prediction and you look for deviations. And those deviations can give you indirect clues to the existence of particles that you haven't yet directly found. And in many cases, they give you access to energy regimes many orders of magnitude above even, the most powerful collider you could conceive of. So you can probe, in fact, energy scales that are orders of magnitude higher than even the super ambitious final phase of the FCC. So it's not just precise measurement, it's also a way of discovering new things indirectly. But that's the first phase. Second phase, which
let me interrupt.
Yeah.
Is most of the cost building the tunnel, or is it all the
question.
Magnets?
The civil engineering is a pretty big part of it. I think it's I should have checked my numbers beforehand. Don't quote me on it. I think it's about 6 billion for the tunnel and the rest for the machine, but I can't. But it's roughly on that divide, I think, something like that.
So if we build the first one, it's still going to cost a lot to build the second one.
Yeah. I'm not sure this 40 billion number. I'm not sure quite where that comes from, but I think the most recent numbers that I've heard are of the order 28 billion in total for the full both phases. But
still a lot.
It's still a lot.
CERN does have a budget estimate, and then the 40 billion come from adding an estimate for the operation cost for the time that the thing would be running, which is in the range of like a billion a year or 800 million Swiss francs per year. So it's something in the range of another billion. So if you look at the cost for the two stages, it's something in the range of 22, and then the operation cost on top, something like that, brings you in the range of 40 billion. This is just, and it's a little rough, but I think it should be roughly correct.
Right. Sabina, let me ask you.
I think he wasn't done.
Harry.
Finish.
Just very briefly. So you have this precision machine at relatively low energy to do precision measurements, and then the idea is if you can make the case. Then after that, you remove the electron-positron machine and you put in a hadron collider. So something like a very large version of the Large Hadron Collider, but with much higher field magnets that get you to higher energy than just the scale increase gives you. And that would go up to energies of about 100 tera electron volts, which is about 7 times the collision energy of the LHC. And the purpose of that machine would be, again, mass production of Higgs bosons, but also a more broad-based discovery machine. So it would be about reaching the highest energies you can, probing the shortest distance scales you can, and seeing what is in this uncharted territory. But that machine, if it happens, would not come online until the 2070s at the earliest, and would run through into the start of the 22nd century. So we're talking about something that is very, very far off. And, if we build the first phase, that is by no stretch any guarantee that you build the second. I think that the focus on the moment is we want to understand the Higgs. That's why we build the first phase. The debate will happen, I guess, sometime in the 2050s or 60s about whether you go to the second phase or not. But that will be a debate for other people to have. I think, most of us will have retired or hopefully still be alive just about. But
Okay. Sabina, feel free to respond to anything Harry's just said. But I want to ask you a question as well, which is, what are the alternatives? Like, if I gave you maybe even half that amount, what would you spend it on? What would be better investment for the money?
People constantly ask me this, and I always say the same thing. You shouldn't ask me. I'm only one person. I have my personal interests. But I really think that the entire community, like in the foundations of physics, should sit together and figure out what's the most promising experiment to do. And now with that preface, I can tell you what I would do. So one thing that puzzles me is that there's very little attention being paid to the measurement problem in quantum mechanics. And I think it's something that we could actually tackle with quantum technologies that are already being developed, but no one's really looking at it. And so this is a problem that I think has practical relevance because it's in a parameter range that we're actually almost accessing, right? We're like, for practical purposes, we'll have to figure out at some point, like, at which size does a quantum system become a measurement device, or what else is it if not the size? Is it the mass, the number of particles? What else is going on? We don't know. So this is a problem that I would throw a few $1 billion at. Because I think it'll unlock a lot of progress that, who knows, might even be useful at some point to build a bigger particle collider. So this is my personal interest. The other thing is that I think it's almost technologically possible to probe the weak field limit of quantum gravity, which would definitely be Nobel Prize winning. So the quantum version of gravitational waves, basically, like in this range, are gravitons real? Like, this is the thing that we want to figure out. And again, this becomes hopefully possible in the near future because of the rapid developments in quantum technologies, where they're dealing with heavier and heavier states and quantum superpositions. Like, there's a new headline like every other week, basically. And there are a few groups working on this, but we're counting 5 people here, 5 people there. And now imagine you have a problem like this, but you have 15,000 people working on it, like they do in high energy particle physics. I think we could sort this out within a matter of years if we had the money and the interest and the motivation.
So, Sabina, I just want to check, are we talking about these we've heard about these tabletop experiments that could try and probe whether gravity is quantum. Is that the sort of thing you're referring to?
Well, that's the question, right? I looked at those tabletop experiments. This would bring us totally off topic, right? But so I think some of them are better motivated than others. Let me put it that way. And the ones that people are currently working on, I think they're not going to deliver conclusive results. And again, I think the problem is there are just too few people working on it. I mean, it's good that they're doing it, don't get me wrong, but I don't think it's going to work out as they think it will. So that there's more that needs to be done, basically.
Right. Harry, so basically there's other areas that have more promise that we're not working on. Foundations of quantum mechanics, potential probes of quantum gravity. Aren't these more exciting? Aren't they better payoffs?
I mean, I'm sure I'm not an expert in these areas, and Sabina knows a lot more than I do. But I mean, my guess is that when you're talking about quantum quantum experiment, talking about low temperature, very sensitive experiments that probably don't require thousands of people. So I think we're comparing two totally different sorts of projects with each other, really. Now, if we need to attract more people into those areas, if it's the case, there aren't enough people working, and that's a sort of separate problem. But it's not a zero-sum game. It's not like we don't build the FCC and suddenly there are thousands of people and loads of resources available for these other areas. The job is to make the case for those areas independently and, gain funding or attract people. If there aren't enough people working in those areas, why is that? Is that because these problems are just not interesting enough and people don't want to investigate them? Is it really because we're gobbling up all the smart people with colliders? Or is it there's not resources available? I don't know. But I think it's a sort of strange thing to think that if we stop high energy physics experiments, that's somehow going to, stimulate other areas of physics that are completely different in terms of the scales, the technologies that they use. So, and I suppose the other thing, these are quite kind of focused problems that Sabina's talking about. Again, I'd make the point with colliders. A collider is like a telescope. It looks at a huge range of different processes, and there you have your key targets. But it's this incredible rich place to do physics. So it's not like you're doing just one thing. I forget how many papers have come out of the LHC, but it's in the thousands now of research papers that have been generated. So these are hugely scientifically productive objects. Now, yes, they're very big, and yes, they're very expensive. But I think personally, they'd pay back the investment in terms of the science you get from them. But I think again, it's not a zero-sum game. We need to be investing in all of these problems, but it's not, trading off particle physics against quantum gravity or quantum measurement problems, I don't think.
Okay, so Ben, definitely respond to that. But there's one other thing I want to, if you can, address is what about some of the other colliders? People have talked about linear colliders and muon colliders. Could you maybe address whatever you want to, what Harry just said about it's not a zero-sum game, and then maybe just explain what some of these other things are, linear colliders, muon colliders, and so on?
Well, so first of all, I want to say I mentioned these two other topics because Phil explicitly asked me to. I didn't mean to say we should take this money and put it into this stuff. I'm just saying I think these are fields which are currently underfunded. And I think more money should go into it. And I actually do think that part of the reason why these other areas are underfunded is because high energy physics is overfunded. So now about this zero-sum game, it's quite funny that particle physicists, they all bring up exactly the same talking points with exactly the same language. And I think there's a deeper reason for that, which is that you all listen to each other too much. And I don't think that this argument is any good, really. I think it's supposed to say that if we don't put these so and so many billion, let's not quibble about it, into this bigger collider, then the money isn't going to magically appear and be available for my pet experiment. Okay, I get it. Okay, but we don't create money, right? So that money needs to come from somewhere. If it doesn't go into this thing, then it will be available for something else. And maybe that's not going to be in the foundations of physics. Maybe it's not going to be what I'm interested in. Maybe it isn't even going to be in science, but maybe it'll be invested into something else that society just values more at the moment. And I totally understand that particle physicists are interested in building this bigger collider and learning more about, I don't know, the Z boson or, whatever your personal interests are. But I think most people don't really care about it. I mean, this is tax money. Like my tax money goes into it, right? Is this how I want my tax money to be spent? And like personally for me, the answer is no. I don't think it's a good investment. And you stated, very confidently that you think such a collider would pay back the investment. Well, I don't think so. And I've never seen any good numbers. Like the only estimate that I've seen about the LHC, which came from particle physicists, so one should take this with a few grains of salt, was that at least the LHC was, had a return on investment larger than zero. Okay. And so first of all, I'm not sure that I actually believe with the estimate that they did. But this really isn't the point. The question is, if you had taken all the money that went into the LHC, like 20 years ago, all those billions, and you had invested it into something else, what would have been the return on investment 20 years later? And I assure you, it would have been larger than that. Okay, so I think this is not a good argument.
I think you misunderstood what I was saying. I didn't say return on investment in an economic sense. I said return on investment in a scientific sense.
Okay, good. Then I just don't know what you're talking about, because I don't see that there's any return on investment that's relevant for anything else than high energy particle physics. And maybe
can I just say, sorry, just saying that, okay, no one cares about this stuff, right? I mean, you could say that about almost any area of science. And also, if you don't make the case that it's interesting, but I mean, I find the opposite. I go out and talk to people about high energy physics all the time, and I found huge numbers of people who are very interested in this. But we all have different tastes. We have different things we're interested in. You're interested in quantum mechanics, quantum gravity. I'm interested in what's going on with the Higgs boson and high energy physics. Most of academia is the number of people who are actually interested in a particular area may be relatively small, but that's not the reason ultimately the government spend money on this thing. It's about a broader case. It's really about is this going to return useful science, for one? But there are also all the ancillary arguments. And I think maybe this is what you were touching on, although I hadn't yet brought it up. When you build these big machines, you are investing huge amounts of money in high-tech sectors. And this generates, returns beyond the actual science of the machines itself. Just to give you one, this is an anecdote, but it's a good example. Years ago, when I was working at the Science Museum, I went down to visit a superconducting magnet manufacturer in the UK. So they took a mixture of contracts from high energy colliders like the LHC. They also made magnets for MRI machines, for accelerators used in cancer therapy. And what they said was they used when they took a contract from high energy physics, they treated it as a piece of funded R&D for them, because often the high energy physicists are saying, build us a magnet with these properties that's never been built before. We need to push it to this high field at this scale. And then they learned to work with new materials, so new types of superconductor. They often actually made a loss on the contracts for high energy physics. But what they then did is took the technology they developed through the high energy physics research and applied it directly. And they showed me a new proton therapy machine they built, which would now fit in a van. These machines used to occupy a huge building, which was they could now manufacture as a direct result of working on high energy particle colliders. Now that's just one example. There are many others you can point to, but it's not just about the science. It is about the direct applications of the technology you develop. But fundamentally, the argument for these things comes down to scientific curiosity. Do we want to carry on understanding the fundamental workings of our universe? Do we want to understand the Higgs boson? You may not think that's interesting. I disagree. I obviously do think it's interesting. But I think, we're not going to persuade each other on the basis of what you or I find interesting, ultimately. And it's up for sort of, I guess, the listeners to this to decide, what do they think it's personally worth an investment? But I would say, again, the cost per person is small. In the grand scheme of what governments spend, this is absolute peanuts. And I think we should be making the case for more science funding as a whole, not to kind of beggar each other's areas of research. We spend far too little on R&D as it is, and we should be making the case for why we need to invest in science in general, together, rather than saying, oh wait, let's shut down particle physics because then maybe there'll be money available for something else.
Sabina?
So I want to clarify that I didn't say it's not interesting. So I made my PhD in particle physics, so it'd be surprising if I wasn't interested in the Higgs boson or particles in general. I'm saying it's not interesting enough for that amount of investment. And so if you say you go around and you talk to people and people are interested in it, that probably means you're a very good speaker and you're a nice person and you generate interest. But I suspect it's also because you generate this interest by talking about those big problems like dark matter, the beginning of the universe and so on, that we already agreed. This bigger collider is very, very unlikely to tell us anything about. So this is kind of weird, tension that I feel when it comes to inspiring people about this sort of research. And about this example you had with the proton accelerator for cancer treatments. Now, imagine how much more efficient that would have been if you had just invested your money into making these proton accelerators smaller. So anytime you put a huge amount of money into a big science project like this, or other science project, they're going to be some spin-offs with the companies that you give the contracts to and so on. So I think that's not going to be specific about the FCC. Okay, so and now you wanted me to say something about other colliders.
The muon colliders and the linear colliders, yeah.
Yeah, so I think to make a long story short, for the other colliders, I think the case isn't that as clearly negative as it is for the FCC. Maybe one thing I should add before I talk about this is that the Chinese also have plans for a collider that's almost exactly the same as the FCC, and I've forgotten what they called it. But
it's the CEPC, I think. The Circular Electron Positron Collider.
Yeah, so it's also a 2-stage project with roughly the same size and roughly the same energy. The difference is they say they can do it for half the cost. So God knows, built in China. So I think this also brings up the question, do we need 2 of these things in the world? Like generally, the Chinese are going to do the thing regardless of what we conclude on our end. And the decision, I think, is due this year or early next year when they make their next 5-year plan or something like this. So this
I think next year is what I heard.
Yeah, that's right.
Yeah. So no one really knows, but I think people should know about this. And so then I think the most serious candidate for a bigger particle collider at the moment would be a muon collider. That'd be a linear collider, not a circular one. And it'd also be optimized to produce Higgs bosons and to study them further. And as Harry said, like the benefit of having so muons are also leptons. So and for all we know, elementary particles. So you don't spread out your energy over composite particles like you do with proton collider. And also, we've never had a muon collider, at least not that size, right? So I think this is why a lot of particle physicists are enthusiastic about the idea with the muon collider. It's a generally new thing. Also, if you're interested in new technological developments, that's the thing to do, because it'll force people to develop some new things. It'd be smaller because it's a linear collider. It'd be cheaper. So I think this is the idea that the Americans are pushing. And I think they called it the muon shot. But I think a lot of Europeans are very sympathetic to that as well.
Yeah. Can I just pick up on
I was done.
So I mean, on the Chinese collider, the CEPC. We don't know whether they're going to do it. I think if China decides to build it, that definitely has an impact on what Europe decides to do, for sure. So, and that will have to be taken into account. It's way above my pay grade to say what happens if that happens, but for sure, CERN will be rethinking their plans, I imagine, in some way. On the muon collider, it's not a linear collider; it's a circular collider, like the LHC, but the So, because the advantage of muons is because they're much heavier, the synchrotron radiation is much weaker. So you can accelerate them to, on a tighter curve without losing all your energy as X-rays, basically. Like the same argument for a proton collider, basically, but fundamental.
There has been a proposal for a linear collider as well. Is that right?
There's the Japanese one, right?
There's a proposed E+ E- linear collider. But the problem with the linear collider is it just can't reach the same intensity as a circular collider. With a circular collider, you have the beams circling all the time. They collide continuously. With a linear collider, you have one shot, basically. The particles go through each other. They smack into the end, and that's it. So you can get to higher energies with a linear collider, a little bit higher energy, but your data rate is much lower. And that means if you want to do this sort of precision work, it's just not as good as the FCC. The muon collider is a really appealing, exciting idea. The problem is the technology is just nowhere near ready to build a machine in sort of a reasonable timescale. So if you want to study the Higgs within our careers, within our lifetimes, then it's probably the only way we're really going to achieve this. Now, for sure, we should carry on investing in these more future-looking muon colliders. There's plasma wake field technology that potentially can get you to much higher energies over shorter distances. But again, these are unproven technologies that require a lot of R&D before we can build an experimental machine with them. So, these are promising ideas. We should carry on investing in them, but they're not going to deliver us physics in a sort of human timescale, I don't think, realistically.
You shook your head when Sabina said about dark matter. Can we go back to that? Because she was saying, we all agree it's not going to make any dark matter discoveries.
I think it's been a slightly caricatured what I said. We all agree that it's not going to tell us anything about the universe or sort of dark matter or the early universe. And that's not what I'm saying. I said we may learn something about dark matter. I mean, in the sense it will tell us what dark matter isn't. It will help constrain the parameter space at the very least, which is a new information. I mean, one thing to say about the LHC, right? Yes, it's not found new physics, but it has transformed particle physics. Ideas that were popular 15 years ago are just, no one's writing papers about supersymmetry anymore. So that is, in terms of, if you define an experiment as one that changes a field, the LHC has been one that changes the field. So non-discovery is still useful information, even if it's not as exciting as saying, oh, look, I've got this new particle or whatever it is. But, the FCC will tell us about the early universe. It will probe the conditions of this Higgs transition that occurred very early on. It will allow us to figure out whether the Higgs transition itself was responsible for creating an imbalance of matter over antimatter that allowed the universe to exist. So it will tell us about early universe physics. It will tell us about various other problems, whether that's through ruling out particular models but primarily it will tell us about this new object we found, which is the Higgs.
Right. Sabina, people are surely interested in the origin of the universe, no?
Well, but this has nothing to do with the origin of the universe. Like in the best case, it's to do with the origin of matter in the universe. Like it's about this particular phase transition. So again, I think that particle physicists make pretty bombastic claims with talking about the origin of the universe, but it's not what people, think it means. Like, even if you're only talking about the phase transition in this matter, you're recreating the conditions of the Big Bang. Like this is like, I don't know how many, 30, 40 orders of magnitude in density away from the Planck scale where we think the Big Bang might have happened. It's also not clear that this, even if you do heavy ion collisions, is it even thermalized? I think it's not. I think it's never been really clarified. So it's not in any sense even similar to the phase transition you had in this plasma in the early universe. So is it going to teach us something? Yes, certainly. If you build a bigger thing, you have higher energy. They're going to learn something from it. But again, the question is this knowledge that society needs at this point in time? Honestly, I think we have bigger problems as humanity as a whole. I think it's not something that we should be investing money into at this moment.
Harry, can you also address that issue Sabina brought up earlier about, well, yes, you've got spin-offs, but you'll get spin-offs in any big project. You build the pyramids, you'll get spin-offs. I think
that's stone cutting technology. I don't know. Yeah. I mean, yes, that's true. I mean, the Apollo program famously points to various things that came out of that. But that's not the point. We're not building the FCC to create spin-offs, but what we are saying is the benefits go beyond just the science. So you get back return on investment from the spin-offs. Well, now, yes, okay, if you really wanted to develop, smaller proton therapy machines, then yes, it would make more sense to invest purely in proton therapy machines, probably. But on the other hand, the thing about fundamental research is it often generates, serendipitous technology that you didn't anticipate. You would never have thought to invest in the first place. So the idea of using protons, for example, to treat cancer, well, that all came out of early particle accelerator research, in the middle of the 20th century. And if that was not done for the purpose of developing medical treatments, it was about understanding, this zoo of particles that people had seen in the 40s and 50s, and then the technology came out of that. So it's this kind of constant process. And now, so yes, you're right. If you really want to invest in a particular technology, that's what you do. But if you don't know that technology is even possible because you haven't made the fundamental investment, then that's not going to happen.
Right. And I want to address this.
Sorry, can I just say one thing? This argument with the serendipitous discoveries is also something that you can make about any big science project. So it's not particular about the FCC.
Harry, do you want to reply to that?
Yeah, but I'm not saying we build the FCC because of the serendipitous discoveries or the spin-offs, but I'm saying it's an additional benefit that helps make the case, right?
Okay, let me go to this issue. And Sabina, if you want to expand on this, I think you've said in some of your YouTube videos that physicists are misleading the public. You see these headlines about dark matter or it's a Big Bang machine when in fact the energy scales of the Big Bang are just Now, do you want to unpack that a little bit, and then we'll get Harry to reply to it?
Well, I kind of already said this, so I'd be repeating myself. So you see this in the headlines over and over, that particle physicists, and I don't mean this personally, I'm sure your lectures are great, and you tell people the truth and nothing but the truth. Honestly, I don't mean to be offensive, but this is what I see in the popular science press, and this has been going on since I was a student. There are these big promises about it's going to tell us what 95% of the universe is made of, or how the universe, why we are here. Like, this is another one of those big taglines. And then if you dig into it, if you know what you're talking about, and unfortunately for many particle physicists, I know a little bit about particle physics, and you push them on it. Actually, your machine isn't going to tell you anything about this. Then they'll admit it, but they'll not voluntarily come forward with it. So the things that make big headlines are like, is this the particle smasher that's going to unravel the mysteries of the universe or something like that? I think that's not okay that particle physicists do this kind of marketing. And then there are people like probably you and all your colleagues who just look away because someone else said it. So, for example, like this quote, which you might have seen me show in a video, it came from Fabiola Gianotti, quoted in a BBC article. So she is still the director until the end of the year, right?
Yeah, you got a few months.
Right. And she says things like this all the time, like it's going to tell us something about dark matter, or God knows. And I actually think the new incoming director, this is a British guy, right? What's his name? Thompson?
Mark Thompson. So he's a colleague of mine at the Cavendish, actually.
Yeah, he's an experimentalist, so he's kind of excused, because I know that a lot of experimentalists actually don't understand how unlikely it is that the bigger collider will find any of these things. They just believe what the theoreticians say to them. But Gianotti doesn't have an excuse. And if you dig into her publication history, you'll find that she actually claimed before the LHC turned on that the thing would almost certainly find supersymmetric particles of dark matter. I think it was supersymmetry. I have all the quotes. And no one ever corrected these things. And that's not okay. And she still goes about and says stuff like this. And of course, people print it on the headlines. And then the rest of the particle physicists are like, it was not my problem.
Harry,
you have to show me the particular quotes, Sabina. But I think what was said, I think there is an argument to be made that the case for the LHC around the excitement of the startup, there was some slightly overblown things that were said. That is true, I think, probably. But I don't think many physicists would have said we're definitely going to discuss. I was only just a PhD student when the LHC switched on, so I wasn't responsible for the press strategy. But I don't think anyone really would have said we're definitely going to find supersymmetry. Maybe there were a few diehard supersymmetry fans who maybe were so convinced it was going to be there that we would see it for sure. But I imagine what most physicists would have said, there is a good chance, if supersymmetry exists, there's a good chance we're going to see it. We will learn something about dark matter. Now, we have learned something about dark matter from the LHC, right? 15 years ago, the dominant idea was this idea of weakly interacting massive particles. So particles around the mass of the Higgs boson that are responsible for the dark matter that we see in the universe. That idea is much, much less in favor now as a result. People are investigating axions, dark photons, hidden sectors, all these sorts of other models for dark matter as a result. So to say we were going to learn about dark matter, well, we did learn about dark matter. I don't think anyone would have said we're going to discover dark matter, though, or at least they certainly shouldn't have said that, because the reason you do an experiment is because you want to find out what's there. If you knew what you were going to find beforehand, why build the thing in the first place, right?
Oh, what about this claim about a Big Bang machine, that it's just nowhere near the energy
I think this is a little bit semantic. So Sabina is talking about the Planck scale. Whether actually the Big Bang even involved the Planck scale is another issue, because you have inflation. So actually it probably never reached those energy scales in the first place. But, it depends what you mean by the Big Bang. So I would sort of think of anything pre-CMB. So up to sort of 400,000 years, you're in a fireball that's expanding. That seems like a kind of Big Bang to me. So you're probing processes that happened in the very early universe when it was very hot and dense compared to today. And with the LHC, you're probing energy scales and physical processes that took place in the very first, sub-nanosecond periods after the Big Bang. So we're not saying, we're obviously not making the actual Big Bang. That would be a very bad idea. But we are probing some of the physics that took place, whether that's states of matter like quark-gluon plasmas that dominated the universe in the first microsecond, whether that's the behavior of the Higgs field that, was taking form in those very early periods of time. So I think it's completely fair to say you are probing the physics of the Big Bang in the early universe. Now, you're not probing time zero, obviously. We'd need like a galaxy-sized particle collider. And even in Sabina's worst nightmares, we're not going to try and build that in the near future. Don't worry. So, but I don't think it's an unreasonable way to describe what we're trying to do.
Okay.
Yeah.
Sabina, do you want to quickly reply to that? And then I've got one last topic, and then we're going to have to wrap up.
Every time I talk to a particle physicist, the Big Bang is moving a little bit closer to the present times. I think like pre-CMB is kind of the latest someone has put the Big Bang in. Look, my point is like most people, when they hear the word Big Bang, they think about the origin of the universe.
Yeah.
And then you can try to water it down and say, well, actually, we're talking about something much, much later than, and so on and so forth.
A trillionth of a second isn't that much later. It's pretty close.
If you look at it in terms of energy scale, look, you know this, right? It's a huge difference.
But I'm just saying, saying it's interesting to know anything that happened after time zero. I mean, that's that's sort of the point.
No, I'm just saying, like, I think it's misleading people. That's what I think. But let me say a little bit about the statements that people made before the LHC turned on. Like, maybe you're just too young to remember, but you should really look at this, because what you said, like, nobody would say such a thing. It was said. And what happens, what has happened in many cases is that there are a few people, and you can count them on the fingers of your hand, okay, who are willing to go public and say these things. Who'll say, the LHC will test string theory. The LHC will find dark matter. The LHC will find supersymmetry, or definitely rule it out. And neither of which has happened, and we knew this, right? Like, sensible people would have agreed that this is possible. But the thing is that there are some people who are willing to say this, the media quotes it, and then all the other 15,000 people look away and don't correct it. And this is the part that I say that isn't okay, that there are some crazy people who are hungry for media attention. I think this will always happen. Like, it's unfortunate, but there's no way to really prevent it.
Can I ask, do you think this is a problem? I mean, I suspect you're probably right that there are a few people who say crazy things that are not backed up by evidence. But I mean, do you think this is a unique problem in particle physics? I suspect it happens in many areas of science. There's this inevitable tension between trying to get, your research publicized. And so, people do probably over-egg it sometimes, for sure. But, I'd like to see the specific quotes from the people you're talking about, because I'm not aware of people saying we're definitely going to discover dark matter. I mean, I find that quite shocking, frankly, if someone actually said that.
Can I just
let me answer this question. Is it the same in other fields? As I said, you have people like this in other fields, but in other fields I see much more pushback. Let me just give you an example, like from astrophysics, where Avi Loeb, has kind of infamously gone about and claimed that this Oumuamua thing that went through, it was an alien technology or something like this, and astrophysicists jumped up in all corners and said, no.
Yeah.
Right? And I don't see this sort of pushback in particles. Actually, I don't see any pushback.
Well, I'm happy to push back now and say we are not definitely going to discover dark matter at the Future Circular Collider. We will learn something about it, though. I will say.
One last topic, and this is something a little bit broader. And I just want to ask the two of you, do you think physics is roughly, broadly, going in the right direction? If so, what should that look like? And if not, why not? And what would be a better direction? Harry, why don't you start off?
It's a good question. I mean, I'm not going to try and talk about the whole of physics because I don't know the whole of physics. But I think, my sense is there's a very broad range of research going on out there, in cosmology, in astrophysics, in high energy particle physics, in low energy particle physics, in dark matter detection. We've got this very broad suite of experiments that are probing, fundamental physics in many different ways. And I think that's a good position to be in. Whether we're doing all exactly the right experiments, I'm just not qualified. I don't have an oversight of the whole of physics to be able to tell you that. But I certainly think in particle physics, at least, which is the area I do know a little bit more about, as far as I can see, having looked at the other projects that we can move forward with in terms of understanding these fundamental questions, the FCC or something like it is the best kind of machine that we can build in the foreseeable future. So I think in that sense, we are going in the right direction. That isn't to say this is the only thing we should do. There are many smaller scale experiments that can teach us a lot about specific sorts of problems, or indeed probe energy scales through indirect measurements. We should be investing in those as well. But I think broadly speaking, as a field, people have tried to come up with the best set of experiments that they can that will get the most information out of nature that we can.
Sabina?
No, I definitely don't think that it's going well in the foundations of physics, and we're not going in the right direction. The problem that I see is that we haven't really made any progress on the big fundamental questions like for 50 years, like ever since the theoretical completion of the Standard Model. And yeah, there have been experiments later, to fill in the details, as Harry said, like with the Higgs boson being the final particle in the Standard Model, like the final nail in the coffin of the Standard Model, to be discovered in 2012. But we have commissioned, like starting in the late 1970s, early 1980s, loads and loads and loads of experiments, all of which have found nothing new. And now, as Harry said correctly, negative results are also results, and they do tell you something. They rule out some part of the parameter space, so to speak. The problem is that there are infinitely many models that you can think of, and you can rule out models until the end of time and then say, oh, we have derived interesting constraints. Okay, but this is not the sort of progress that we're looking for. We actually want to find new physics. And I think what's missing in the foundations of physics is that the community comes together and has a hard look at what went wrong there. Like what went wrong in the 1980s that we haven't found anything new since. Like, except for the stuff that we already predicted earlier, as I said. And I think basically the reason is that we're not careful enough with thinking about what experiments to invest into, which is exactly what we're talking about now. And at the present moment, investing a lot of money into building a bigger particle colliders isn't going to get us anywhere. We'll have to think about what's the thing to invest into that actually has a huge potential to deliver data for new physics. And this is why I say we need to think about the measurement problem in quantum physics. You said earlier, like, okay, we just have different interests, and we're not doing this to benefit society or something like this just for the knowledge discovery. But if you think about the measurement problem, I do think that solving this problem would have technological implications. The same cannot be said about, measuring the properties of the Higgs boson, for example. So I think there are very good cases to be made that some experiments are more promising, more relevant than others. And so we have to think about in which order to invest money so that one builds on the other. But that's not happening. Like this self-reflection of the community just isn't happening.
Okay, well, look, we've run out of time. We let Harry start, so we're going to let Sabina finish there. Thank you so much, both of you. It's been a really fascinating conversation. If you like this content, please give us a like, subscribe to the channel, and we'd love to hear your comments. Put them in the comments. And thanks again, Harry and Sabina.
Thanks, Phil.
Thank you.